I'm really thrilled to introduce this panel, which is really mostly going to deal with how quickly stratospheric aerosol injection could start, though in Q&As we may get to some other SRM technologies. So first, to my left, we have Doug MacMartin. He's an associate professor of mechanical and aerospace engineering at Cornell, and really just an amazing colleague. And also, just kind of for fun, it's of interest to me that Doug and me and Ted Parson, who is somewhere in the room, all grew up in Ottawa, though in different high schools at about the same time. There might have been something in the water. Next, we have John Langford. John founded Aurora Flight Sciences back in the late 80s, I believe. It grew to be a kind of 500-person scale company. He sold to Boeing. He started another company that did some controls. He sold to Rockwell Collins. He now runs a company called Electra.aero that's just developing a short takeoff electric commuter aircraft. He's the past president of the American Institute for Aeronautics and Astronautics. And finally, we have Wake Smith, who I hope can hear us and is appearing now, but I'll start introducing him anyway. Wake Smith was an aviation executive who worked in several major companies and PEMCO Aviation Services at the end. And I think it's fair to say that Wake is a absolutely stunning example of what successful retirement looks like. So Wake retired from these commercial aviation jobs 15 years ago or something. I'm not going to get exactly right. And he's made an amazing impact on this field, publishing a lot of papers, collaborating with many of us, and writing one book and I guess another one in development now. So it's really an amazing panel. So how quickly could SRM start? I think that's an important question, but I want to be very clear that this is setting aside other very important questions that we're not dealing with right now, like, is it a good idea? What are the rules around it? What countries might do it? Those are things we spent a lot of time talking about in this meeting, and I'm not going to be talking about them, or we won't be talking about them in the next little while. What we really want to talk about is how feasible it is to start. What would it cost to start? And that depends on what it is and how it is done. And I propose to give you a framework which will help resolve some of the uncertainties here, a framework with 4 acronyms: BBAU, WPB, SRE, and FRI. And with that acronym soup, I hope to clear up some underlying confusion, because in the community here, there's been wildly different views expressed about how hard or easy this is, with some people and papers suggesting this could start in a year or two, and others suggesting that it might take decades and cost $100 billion class dollars. And I think, in fact, there are arguments for both those that are correct, and they depend on assumptions. And I will try and give you a little framework about that before I turn it over to the others, explaining my silly acronyms. So 2 of the acronyms, it's a 2x2 matrix, are about what it is. So and the central question is, how quickly is cooling ramped up? There's not a right answer to that. It's a policy choice. Obviously, some people might say the answer should be never. We shouldn't be doing it. So if you say that a slow ramp with efficient SAI, and in the last talk, there were evidence about how we might be able to do it efficiently using gases that are high sulfur content gases and clever ways to control the particle size distribution. If you ramped up at a 1/10 of a degree C of cooling per decade, and to use efficient SAI, then the way to think about it in terms of the aviation need is you need to deliver, starting at 0, after 1 decade, you need to deliver about 150,000 tons a year to the stratosphere. So from the aviation purpose, that's kind of what you need to the high stratosphere. The other extreme would be a fast ramp and low efficiency. So if you wanted to cool by 0.3 C per decade, which would actually be adding cooling faster than the world is now warming, so you'd actually be driving temperatures down, and you're doing it with SO2, and you're doing it inefficiently, then you need something like 12 times more material, so something like 2 million tons a year after a decade. Both of those are plausible assumptions under different conditions. Now my other 2 acronyms, BBAU and WPB. So BBAU is bureaucratic, business as usual, and these are acronyms that have to do with how the contracting is done. And there's no simple answer to that. But to give you a sense of what BBAU might mean, the U.S. wanted a new aerial refueling tanker, which is now called the KC-46, which is derived from a 767 commercial aircraft, which works just fine. And it took 18 years from the time the contract started till it entered service. And that's for what, to me, as a non-aviation person, seems like a kind of minor modification to existing aircraft. On the other hand, the other acronym was WPB, by which I mean the War Production Board, the famous thing in World War II that allowed us to make so many things in the U.S. so quickly to supply Europe in the early part of the war and Lend-Lease. And this isn't actually an example from that, but I'll give you the example of the U-2 aircraft, which from project start in 1954 flew the first operational spy missions in the stratosphere in 1956. So that sort of spans the range of what's fast or slow in aircraft development. So that's all I want to give you as a summary, but the point here is there's a 2x2 matrix. How quickly does it ramp up, and what are the contracting conditions under which it's done? And I think lots of the disagreement around this is really about different of these assumptions, not disagreement about the underlying aviation. But now I'm going to turn it over first to Doug, and then to John, and then to Wake to start talking about the actual aviation and modeling.
Thank you. Thank you for the introduction. And I've forgotten the specifics of the acronyms already. As I'm sure as everybody
They
else.
were kind of, what I hope is clear is the 2x2, not the actual acronyms.
So let me just start by, I think lots of people, when they think about research in this subject, it's basically like we're not ready to deploy. Why are we even talking about how would you deploy? I think David laid out an excellent case purely on the governance side. It's important to understand how fast you could deploy, and it's also important to understand what actors are capable of deploying. The other thing I would say on that is, if you're imagining X years in the future and you get to pick X, and you want to be in a position that you can feel like you're making some informed decisions about deployment or even about governance, you want to know what's going to happen. And you want to know what are the uncertainties in that? How confident are we? And I would say both of those also depend on how you're deploying, right? You can't say what's going to happen and what the uncertainties are without saying the impacts of what, right? So you have to specify a deployment pathway. That means that we actually do need to pay attention now to a lot of the questions about how you would deploy it. So if you're envisioning deploying, I think sort of an obvious question is the aircraft of like, how do you loft the material up? But if you're imagining, okay, I want to go deploy, you need a supply chain for sulfur or whatever material you're using. There's a whole pile of ground infrastructure you might need. You need to figure out, how do I put this on the airplane? So tanks and all of the safety for loading and unloading and so forth. What's the airplane itself? And the con ops and everything associated with that. How do I get the material off the airplane? And that, by the way, has some implications on aerosol microphysics. If you were in the room this morning, there was a little bit of conversation about the challenges of even getting solid aerosols off of an airplane at any reasonable rate, for example. And then once it's up there, you need to be able to monitor it, right? So you need a whole pile of in situ observations. NOAA right now has an instrument suite on an airplane. I think you're going to need more than one. And you need all of the satellite observations in place to tell you what's going on. And then you need a plan that says, what are we going to do with that information, right? Even the day that you deploy, there's going to be a bunch of models. They'll say slightly different things. We don't know which one's right necessarily. As soon as you start deploying, you will start getting information first in the stratosphere about what's going on that allow you to say, either this model was right and that one was wrong, or, whoa, all of the models are out to lunch. And you use that information. You need to write down a plan that says, we're going to measure X, we're going to compare it to what we think is going to happen. If condition A, we might just stop. If our models are completely out to lunch and rethink, right? So you have to actually, if you want to deploy in any responsible way, you need something on all of those. And you might look at that list and you say, well, some of those just sound like throwing money at stuff. I will say, even something that seems easy, like the ground infrastructure, My personal view would be if you are lofting something like sulfur dioxide or H2S, you are not doing that mixed with commercial traffic. You are not doing that anywhere where people live. And that may actually mean that you're now thinking about, oh, I have to build an entirely new facility with runways, access to deep sea ports or railways, et cetera, et cetera, et cetera, right? Like, so there is, when you're thinking about how long does it take to deploy and what actors, there's a bit of this other stuff. Second really broad thing, I would say there's a fundamental dichotomy in how you start, depending on whether you're thinking about using new airplanes or retrofitting existing aircraft. Traditionally, most of our simulations, we've put stuff in, material into the stratosphere somewhere in the tropics where the tropopause is relatively high. You need to get to like 18 to 20 kilometers. That requires new aircraft that don't exist today. John is about to tell you that that's not fundamentally hard. At higher latitudes, the tropopause is lower. Gulfstream business jet type aircraft can get to about 15 kilometers. I flew here at about 10.5 kilometers, according to United. We also commissioned, at Reflective, we commissioned a study with Aerotech on aircraft modification. And it seems actually reasonably likely that for a few $1 billion, you could re-wing a 747 and actually get pretty substantial payloads, like 60, 70 tons per flight, up to more like 16 kilometers. So that represents an alternative. You cannot deploy between about 40 north and 40 south because you're not in the stratosphere. But you could deploy at higher latitudes using existing aircraft. And then that basically says, okay, well, there's an alternative, plausible pathway for how you would start. And you can go into it. Now, what's the right answer? I don't know. It depends on what are the comparative impacts. If you're deploying at high latitudes, you're effectively going to overcool the high latitudes relative to the tropics. That's not, if you care about ice, that's maybe a good thing, but it's not obviously a good thing because you change temperature gradients. So it depends on that. It depends on how soon you want to deploy. It depends on how hard you think it is to develop new aircraft. Depends on how hard it is to modify existing aircraft. So there's a whole lot of things that we quite frankly don't know. And some of those are value judgments on which of those options make sense. My personal view would be you would never want to do a lot of cooling at high latitudes, but it may be a plausible path that's worth at least understanding so that you can provide options to policymakers. Okay. I actually do want to address one other thing, and that is if you were in the morning session on SRM, some of you, Ming-Yi talked about uncertainty in the aerosol microphysics. My default assumption has generally been the near-term deployment would be lofting sulfur dioxide or H2S. I don't really care. Or from an aerosol microphysics, if you loft sulfur directly, that has insane benefits on safety. SO2, by the way, and H2S are really nasty. They're fine in the stratosphere, but you don't want to. You can deal with them in industrial settings, but you don't necessarily want to be around them. When you release that, first thing that happens is it gets mixed up in the aircraft wake, and that dilutes that material somewhat. It is still vastly more concentrated than in a volcanic eruption. So right now, we calibrate our aerosol microphysical models off of observations from volcanic eruptions. Those are not exactly even controlled tests. You'd say the aerosol microphysical models kind of do okay-ish, but there's uncertainty in the observations, there's uncertainty in the initial conditions, and an airplane is not a volcano. Right? So it gets mixed up in the initial wake. It then gradually spreads in the stratosphere. That plume gradually gets stretched into thin ribbons. Diffusion gradually mixes it out. Those are all uncertain. And then the oxidation depends on concentrations. once a molecule of H2SO4 forms, either it adds onto an existing aerosol or in principle nucleates new aerosols. That ratio depends on background concentrations as well. There's a pile of uncertainties in there. We are actively trying to think about what set of experiments could resolve that. You can imagine ways of getting at each of those pieces, but ultimately you probably want to go fly an airplane, release a pile of material, and actually say, do we understand what happened? Do we actually get our model predictions correct? Imagine like a 10-ton or 5-ton. I don't actually know what the correct number is. The reason that's relevant is as soon as you start thinking, hey, actually, all of this time modeling, we've been ignoring all of the small scale stuff. David's been bugging me for a decade saying you're ignoring the small scale stuff. He's right. I finally caught up to that line of thinking. Thank you for being persistent. As soon as you say, oh, wait, actually, let's think about doing that experiment, you immediately also have to engage with all of these questions about how are we actually going to go do that? How are we going to put sulfur on an airplane? How are we going to get it off? What airplane are we going to use? How are we going to track the plume and so forth? I think I hit all the points I was planning on hitting.
John.
You've got slides, right?
So I was going to talk a little bit about what I think the capabilities, the constraints, and how we would get there, basically based on some questions that David asked me after the workshop we had a little over a year ago. I think it's important just to give a little context for this because, as David said, there's a couple of ways you could approach this problem: the sort of big company, business as usual, or the smaller startup approach, representative of Scaled Composites, AeroVironment, or Aurora. I come firmly in that smaller camp, so I'm going to give you that perspective today in this. My career has been focused on low Reynolds number airplanes, things that fly either very slowly or in thin atmospheres. We did a series of human-powered airplanes all the way up through planetary aircraft, and today I'm involved in a company called Electra, which is doing focus on decarbonization of aviation. There's a hybrid electric passenger airplane we're developing, but we're also continuing to focus on the issue of stratospheric. A stratospheric observatory. It was brought up earlier that there are in-place ocean monitoring networks, a backbone. I think Alicia was talking about on that. There's no such thing in the stratosphere. That does not exist today, and it needs to. What we have is what David Fahey and his colleagues have done. We do short excursions up to the stratosphere, but we don't stay there, and we don't have a comprehensive in situ monitoring. So we've taken a piece of the electric airplane company, Electra, and we're spinning out a focused sister organization, which we call IRIS, which is focused on three things initially: the wildfire prediction, detection, and tracking. That's primarily being driven by Jim Anderson up at Harvard. The whole ice sheets, the glaciarization process, working for Brent Minshew at Caltech, and then the SRM working with David and a number of you here. To do that, you have to have sort of three key elements: the instruments, the data analysis, and the platform. Today, the scientific colleagues and our relationship is strongest with Harvard today. As David was saying, I think I started out working for Jim Anderson in the late 1980s, and Jim is one of those people, when you work for Jim for a while, you always work for Jim, and so he's still doing the instruments, and a lot of the analysis is coming out of Harvard, and I'm focused on the platform, which is a solar powered robotic airplane that we're doing. And there's really two SRM projects that we're focused on. The first is that question of how do we measure, how do we establish the science, the chemistry, the radiation, the dynamics, so that we can actually validate models and know what we're getting, right? It's establishing that truth. And that requires the observing network, the long-term, many different measurements around the globe in different parts of the stratosphere. And for that, we're developing the solar airplane. the SAI platform that David asked us to take a look at is like, well, if you were going to put a megaton of aerosol into the stratosphere, how would you do it? And I want to share some of the answers we've developed over the past year working on that question. The first airplane is really focused on that need for in situ observations. I won't go through all of that, but this is an issue not related just to SRM, but all kinds of things. Critically, the questions of ozone depletion and how the addition of things into the stratosphere might affect that. There's again, a lot of the lessons come out of Pinatubo and the volcanic eruptions, and definitely SRM works, but it had some pretty some adverse side effects as well, particularly for the ozone. This is the platform that we're developing. We first flew it in September of 2022. NASA and a private foundation called the Weld Foundation have supported its development, and we're currently upgrading it for stratospheric tests. This is what it looks like. The figure on the left, lower left, is sort of what we think we can do in terms of today's performance of batteries. One of the big drivers of this in a solar airplane is you can only fly where there's sunlight. So you're both latitude and time of year dependent. But the main driving technology of this is your energy storage density. And the left is sort of what it is today, and the right is what we think it will be as the NASA and Department of Energy programs that are underway bear fruit over the next few years. I was this morning at 9 o'clock doing at the NASA DOE battery workshop down at Argonne that is focused on exactly this question. The other piece of it that has been alluded to is the need for instrumentation, right? One of the ways you make less expensive, lighter weight airplanes or platforms is that you invest significant amounts in making lighter weight, I won't say autonomous, but automated instruments, much as we've seen the small satellites, so the small sat revolution, CubeSats, over the last couple of decades. In addition to the sort of grand observatories, we need a similar thing on the aviation side. Switching to how would you put a megaton a year into the stratosphere, this is sort of where we come at a first sort of concept design look at that. The approach we would take would be unmanned to do this robotically. It would be built of modern composite materials, and very significantly, it would use an off-the-shelf proven engine, because as soon as you start talking about engine development or even engine modification, you really get into hundreds of millions of dollars on that. Fortunately, there is an engine that you can buy off the shelf. It's a Rolls-Royce engine made in Indianapolis. It's called the AE3007H. It flies on the Global Hawk, which is today an Air Force and a Navy platform, but it's also on a couple of different commercial platforms. There's slight differences between them, but the key is that it's in production. And in this study we've done over the past year, we used both sort of published textbook data, which is shown here, but also brought Rolls-Royce into the program, and we got to use one of their actual proprietary engine decks on this for the modeling, and so there's a lot of advantages to having something that is in production today in terms of both time frame and cost. This airplane is designed to carry about 7.5 tons per flight, go to 20 kilometers, and the other sort of significant thing that we're looking at is housing the aerosol in a swappable conformal tank so that you separate some of the airplane issues from some of the logistical operations issues that Doug was talking about, particularly given the uncertainty of exactly what we're dispersing. And some of it, like the SO2, as has been mentioned, is pretty nasty stuff to handle, and it's well suited for an unmanned and separating the airplane side from the dispersant side. These are just some things of what it would look like. It essentially is a twin-engine airplane, not too different from the Teledyne Ryan and then Northrop Grumman Global Hawk. It's a pretty short mission. The Global Hawk stays up for many tens of hours, but this airplane would do like a 90-minute round trip. It would take off, fly to altitude, and then do a dispersal mission over 100 miles or so. That was not a design criteria, and there was it's designed to do dispersal sort of near its operating base. It's easy to ferry the airplane long distances if you swap the conformal tank for fuel tank, but for the operational mission, it has a relatively small amount of fuel. Here's a comparison of Global Hawk, the concept study we're doing, which we call the IR-1, and the sail concept that Wake will probably talk about in a minute, that he and a number of colleagues have done a couple of AIAA papers on. But the idea is that it's the composite airplane is smaller and lighter, carries less payload, but it does this fairly short up and back mission. We think an airplane like that could be fielded in a prototype level, which would mean sort of 2 airplanes flying, doing the demonstration mission for on the order of $120 million, and that's based on a development approach that essentially, and numbers that we developed at Aurora over about 30 years of doing this. It would operate under an FAA special airworthiness certificate, so it would be constrained in where the tests could take place. They wouldn't be overpopulated areas, and it wouldn't be for commercial operations. But if we come down in about the 120 million or so, and that very much assumes that you're buying that engine from Rolls-Royce. After that, it's probably around, and this gets a little fuzzier, in rate production, 20 million or so a copy. There's some commercial airplanes. I mentioned that this engine is on several airplanes. Well, that's sort of what those airplanes cost, the Embraer regional jet and a Cessna, a Citation 10 business jet. And so there's a lot of stuff on this that is not on, there's a lot of stuff on a human carrying pressurized commercially rated airplane that is not on this aircraft. It's unpressurized, which is a significant difference. And we think there's around 300 of these that you would probably need in the fleet. There's a lot of assumptions about lifetime and hours and stuff. This includes $1 billion in that program for what we would call an EMD program, which is taking prototypes and turning them into production and getting them a commercial certificate. What would it cost to fly this thing? Well, the bottom line is the direct operating costs we think are going to be, $4,600, so around $5,000 an hour. And if you account for depreciation of the asset in that, a little over $7,000 an hour, and you can there's some comparison numbers there of what the commercial airplanes cost in that. Obviously, fuel cost is a significant number in this, and we haven't included some of the things Doug was talking about basing and insurance and stuff like that. So the bottom line on that is a little under $1 billion a year to run the loft, the megaton of aerosol. And then if you do that over 10 years, that's about a $15 billion price tag. And I would stress that this is, a preliminary concept study based on the discussions at the last workshop, but it gives you a sort of sense of where this could go. And to put it in the final context here, this is an enterprise that is somewhere between Cape Air and Spirit Airlines. We're not talking United Airlines. We're not talking FedEx. We're not talking the U.S. Air Force. These are things, people who have, fleets in this size do the same number of operations in this side. Spirit had about 17,000 employees when they shut down. Cape Air has about 800, so you can tell there's a big difference in sort of how those airlines are set up. And our assumptions have about 3,000 people in this thing operating at rate, just to kind of give you a sense.
Thank you very much. We can take the slides down and get Wake Up. And just to tie that back to my silly acronyms, so my I've got to check the acronyms myself, of course. My slow ramp efficient case would have needed about 150,000 tons a year after a decade. So that's almost 10 times less than the million, or 7 times less than the million tons a year. But the fast rate inefficient case would have taken 2 million tons a year. So the kind of case that John was talking about of doing 1 million tons a year is sort of in the middle, but there are certainly credible deployments that would take much less than that and therefore less cost and less aircraft. Wake.
So thank you kindly, David, for hosting me remotely on this panel. I'm thrilled to be able to participate with this august group in this discussion. Much of what I might have said has already been said, and so I won't repeat that. But firstly, to present a bit of information about the SAIL aircraft that was earlier referred to. This was the Stratospheric Aerosol Injection Lofter 01, or sort of the first look, I think, in the world at a detailed preliminary design for an SAI Lofter aircraft. It's different than the IR one that John has just been discussing in a variety of ways, but similar in other ways. Firstly, it's another tube and wing aircraft like the IR one, like most aircraft are. It was designed to carry about 15 tons, so twice what the Iris would carry. It too went to 20 kilometers, carrying SO2, very short out and back mission, as John had mentioned. The SAIL is based on the other engine that is currently known and certified to operate to these altitudes, which is the GE F-118 engine. That is a military-only available engine, so the SAIL isn't an aircraft that one could really go out and build because the military likely won't sell you that engine. But the purpose of the SAIL design exercise was to try to demonstrate that one could build a Lofter aircraft for SAI that could haul stuff to 20 kilometers in the tropics and could be fully built from pre-existing engines, wing planforms, avionics, and so on. There was no unobtainium that was required to conceptualize the SAIL. And I think the same is true of the IR-1. So the IR-1 is another confirmation that this aircraft is reasonably buildable from technologies that already exist. There aren't big technological breakthroughs that would be required to do this. It is essential, as John earlier mentioned, that one at least note the engine issue. If one is simply building an airframe around an existing engine, that's a much smaller work scope than if one needs to design a new engine. And at this point, there are only a couple of engines that serve. The good news on that front is that we're not commencing this program right now. One can guess that the last panel ended with people guessing how far into the future this is, but a green light, properly funded decision to begin to build the SAI deployment fleet. We can debate how many decades away that is, but it ain't happening immediately. And so the point is there may be new engines that will become available by the time we're trying to ramp such a thing up. 6 years ago, when we developed the SAIL plan, the drone technology and drone certification requirements were much less far along. And so we assumed that the SAIL would be in situ piloted. Certainly, the way this mission will be flown in the future is as a drone or at least remotely piloted aircraft. So that's certainly another development that the IR-1 gets right as to how this might unfold. To me, though, a main point to be made about this whole discussion is that unless we're in some climate emergency, and I think that the climate emergency framing is mostly unhelpful and unlikely. But unless we're in a climate emergency framing, I don't think that it is the building of the aircraft that will pace the rollout of an SAI program. David, you mentioned at the outset, these are things we're not going to talk about, and so I won't much dwell on that. But once again, as long as we're not in an emergency framing, the aircraft requirements ought to be able to catch up to the broader thinking about whether to do this and when to do it and how to do it. It's also been mentioned earlier that it's possible we're starting at high latitudes rather than in the tropics. And if we're undertaking that HILA approach to at least the commencement of solar geo, that's a much easier flight requirement. We're almost certainly talking about modified versions of existing aircraft rather than the novel aircraft that would be required to deploy at 20 kilometers in the tropics. As Doug earlier mentioned, it's also important to remember that the aircraft, the deployment aircraft, are not the only bit of infrastructure that would be required. The requirement for potentially dedicated aircraft, or airfields, or at least the requirement to operate from non-civilian, i.e. military airfields, that is another infrastructural requirement that will also have substantial timeframes tied to it. In terms, though, of David's sort of starting question of how quickly one could roll such a thing out, a couple of variables that matter hugely. Firstly, is HILA versus tropical, but another one is who the customer is. To the extent that the customer is the U.S. government or a major government such as that, the Chinese government, they could mandate that this be a military program rather than a civil program. And the military programs, the tanker aircraft that was earlier referred to is an example of how that can go very slowly. But military programs could also go much more quickly. There are at least much more streamlined certification requirements that can be brought to bear in respect of a military program. And so it will, the speed at which something such as this could be developed will depend greatly on who the customer is and what certification path that means is available to the program. If we're certifying under an FAA or EASA civil cert path, that is tougher to expedite. Again, if we're certifying under a military program, there may be more options to expedite. Perhaps I'll stop there.
Thank you very much. I'm going to take chair's privilege and ask John a question or two, maybe get a short conversation here and then turn it open to the floor. So, John, I guess my first question is, let's say, politics aside, let's say somebody had the money and wanted you to start building this aircraft. What would be the rough time from the time that you had the contract to the time that you'd expect to fly one?
It would take about 36 months from the funded start to having those two demonstrator aircraft, which are functional prototypes, so they'd be able to do the dispersal mission. So 36 months is I think, consistent with what we've seen in the past. Maybe a little bit less, maybe a little bit more, but 36 months on that. And then it's probably an equal amount of time if you wanted to then launch an actual production effort. It's probably another 36 months before you'd be able to see what we call conforming aircraft coming off that line.
And as I recall, Wake and I, in different ways, asked you these same questions when we had you first showed us this design a few months ago. But the basic question was, to be blunt, kind of, why should we believe you? Because there's lots of evidence of cost overruns, and there's military aircraft that took a long time. And of course, your company was involved, as I recall. Aurora did make part of the Global Hawk.
Absolutely.
So I think I want you to just give whatever answer you want, but kind of answer you gave before that kind of justifies why this looks different from some military programs you've been part of.
Well, I think there's a lot of evidence as you look at sort of the portfolio of what Aurora's done, what AeroVironment's done, what Scale Composites has done. That's the evidence base that these numbers are drawn from. They are at this point still parametric, right? For this class of airplane, what is the sort of cost per pound and things like that. But there's plenty of experiential evidence of those programs being done. As Wake was saying, in some ways, you're only an executive order away from launching this, right? I mean, one of the amazing things in the crazy world is how fast longstanding institutions can be destroyed and how fast new programs can come out of like almost nowhere. I think backing that up is what we've seen in Ukraine, and the rapidity. It has been a while. It's hard to believe that started in 2022, but weapon systems that were not developed in 2022 are now being fielded in Ukraine, and I think that shows, to Wake's point, the system can move as fast as it's driven in these things.
So the summary that I would offer is that if this is done in a BBAU, bureaucratic business as usual way, and if starting means starting with inefficient and really large cooling, then it really is something that could easily take a couple decades to start. And it's also true that if starting means starting at this lower kind of ramp rate and efficient, and if it's done in a more efficient way, not necessarily the full war production board, but just the kind of efficiency that we've seen in lots of examples of, then it really could start in just a couple of years, which means that the gating thing is really not the technology. So with that, I welcome questions, challenges to my assertions. Wake, yes, take a comment from Wake right off.
Great. What John has said, the prototype and 3 years to commencement of production. I think there is a fair amount of history to that under a military cert program. What often causes military programs in particular to take so much longer is that the government is often a very fickle customer and changes its mind midstream. And if we have multiple governments involved, because this is a joint program with the EU and the US or whatever, there's yet more opportunities to change one's mind. So these very fast assumptions rest upon the assumption that the customer is focused and decisive, and governments sometimes do that. The literal wartime example, they make decisions very quickly, and in other times it's in which state is the landing gear going to be built, and whether this, and it gets into normal politics, which slows things down.
Assumptions drive the answer. I see Dave Hawkins.
Yeah. This may be a low probability scenario, but have there been any modeling of potential exposures in an aircraft crash incident with a payload of sulfur, either exploding at 1,000 feet or hitting the ground and exploding?
Yes, there have been. We paid one of the best sulfur safety consultants to do such a study, and that study will be an addendum to a paper, which I think, is Jim in the off room, is accepted or no? They said one paragraph? Basically accepted. We can send it to you in ES&T. So yeah, and I should say, as an Albertan, it is true that these are very toxic substances, but it's also true that people work with them every day of their 30-year careers and expect to be safe. That is, in Alberta, we have multiple places where we handle literally million-ton-a-year scale of these chemicals. And yes, there have been fatalities. That's what started Pembina, an environmental group that I care about a lot in Canada. It was actually started by a gas fatality, but that was 30 years ago. And in general, these things work. There are many places in the world where we literally handle millions of tons a year of these chemicals in a safe way.
Thank you all for a great panel. I think excellent questions. As you may surmise from my hat, I'm part of a group that really is concerned about the urgency. And I mean, uh, uh, for example, we're losing coral reef because we're not cooling fast enough. And we could do that, for example, by just relaxing IMO emission controls on the around the Great Barrier Reef. But so to that point, would it be possible? I mean, the idea of the high latitude deployment, the polar deployment, is to pilot. It's a place where you might pilot, and I know David and I think Wake did a paper on that possibility to do a small scale kind of localized piloting effort in the polar region, because that's one of the few places you could do that because of the circulation up in the stratosphere. So I would like to ask a question on that, and also to just really I think the urgency of this is something we really, really have to have foremost in our mind. So I would really urge, uh, uh, you know, uh, doing the testing, the science. We all love that stuff. That's really important. We need to do as much of that as possible. But if you're doing that in the meantime, you're losing reefs that will never come back or humans that will never come back.
Question?
That's so that my question is, uh, what about doing testing and piloting in the polar region, starting slow, also to build acceptance.
Good. Got it.
Through that,
I think
through that
Doug's the
method.
right person to address that.
Yeah.
I mean, I would say that was basically one of my bifurcation things you can in principle start with new aircraft, but there is still a bunch of stuff that you would do even there. Could you be doing some meaningful cooling in 5 years? Probably, but that would probably mean short-circuiting some of the more responsible science. I mean, aside from all of the public legitimacy issues and so forth as well, right? So
Liz at the back.
Yeah, I wanted to ask a question and push back a little bit on the observational platform. Like, more observations are great, more aircraft are great, but 30 kilograms of payload is pretty tiny relative to what goes into a modern scientific study. Like, I could see you can get some particle size distributions, a little camera, maybe a filter collector, but beyond that, like, you run out of payload fast. So I'm wondering, I just want to emphasize to the community here that is 30 kilograms of payload is not a sufficient observation platform in general. It's an addition. And I just wondered what you'd put on that size of payload. What was your actual plan for that?
Yeah, you can't do business as usual on the instrumentation. Most of the instrumentation that flies today is essentially laboratory heritage. It's built in the lab, it's calibrated in the lab, it's put out on the airplane. And in the case of the DC-8 or coming up on the 777, it brings its scientists along with it. That's not how you can't do that in the future if you want to operate at scale. You have to do much more in the small observations. And these, we have papers and studies that show what you'd get for the whole 30 kilograms and how you package that. But I don't dispute that you have to have, a fundamental assumption is that you have an instrument development and miniaturization program. But that's long overdue as well. That's not that hard to do. So be happy to talk with you offline about
So
that.
John presented this solar aircraft as the study aircraft and the deployment aircraft separately. But of course, that's not written in stone. John's the aircraft designer, not the instrument builder. And there's certainly ways you could imagine John or some other of his competitors developing something like what you saw as a deployment aircraft as a science aircraft. Indeed, Oliver Morton has pointed out to me, and many of us know, that there are really only a very small handful. We just, I think, damaged one. So maybe there's 4 operational aircraft now that fly in the stratosphere for science, and they're all owned by Americans, and some of us are distrustful of Americans and might like to see Europeans have an aircraft like that, and that's the kind of thing that could conceivably be built.
I'm kind of curious about some of the assumptions that are going into it. I'm thinking about Ukraine. So it's true that they developed the drones, and they've developed a lot of new technologies, but the mission failure rates of these systems are pretty high right now. So I think what I've read is somewhere between 1 in 6 and 1 in 3, some component of the drone malfunctions, but they swarm, so it doesn't matter that much. I'm also thinking about what drives costs is that I mean, I've had friends of mine at NASA that said if we were allowed to blow up things the way SpaceX was allowed to blow up things, we could make things cheaper too, right? And so I think it does matter what you're thinking, how you're conceptualizing failure rate, and what constitutes acceptable attrition within the fleet and that kind of thing. That will affect costs. Have you thought? So, what are your thoughts about those kinds of factors?
I'd say that's over to John, and it's really a question about the gap, as I see it, between these kind of really one-offs that Scaled has built and more operational aircraft.
Yeah. Well, first, my comments on Ukraine were not that technology is at all analogous to this, only as when pushed, the system can move very fast, right? You can go from nothing to 1 million a year of, reasonably sophisticated things, but I don't mean to imply that those drones are anything like what we would necessarily be flying.
Yeah, I mean, I guess, and tell me how different the operational fleet would be. I mean, a critique one might offer of your stuff is that an operational fleet really looks different from the first aircraft that you guess will fly, but are not. Yeah.
Yeah, I mean, to the point about NASA versus SpaceX, there's a lot of levels to that discussion, right? About what are the real organizational incentives that are going on in each of those. I will say, when you're paying your own money, you do find ways to do it less expensively, right? And so the point that was raised about requirements creep of a government program is very real, right? When you have a consensus program, the requirements build up. When one of the things that Musk does is ruthlessly strip away requirements, and that is one of the sort of foundations on which they've been able to build the program. The failure rate that you're willing to tolerate is definitely something in there. It depends on who's doing it and what the sense of urgency is. It has to all be weighed. It's like the autonomous driving, right? Are there accidents? Yes. On net, does it save lives? Also, yes, right? And so that any of these technologies are going to have challenges, and you have to be, I think, open and deliberate, transparent about how you're optimizing that system.
I would just add the number of flights that you need to do this. Even if you get the failure rate down to like 1 in a million commercial hull loss numbers, you're going to have accidents during a program, which is why I would say you don't want to be doing this. You want to be doing this in somewhere really remote. Your runway goes out into water, unmanned aircraft. If you lose one every few years.
So I want to get one more question. I know I've got Pete Irvine, and I might take two, especially if it's somebody I don't know I want to give to. So how about Pete, quick question, and then this gentleman, a quick question.
Yeah, I was just wondering for John, are there stepping stone use cases for those first pilot drones? Because at the large scale, you're talking many tens of billions, but for the first thing, it's 120 million. Could you use those for something?
Let's get both questions first. Go ahead.
Wake made, to me, a very provocative comment about emergency framing is not desirable or necessary. And I'm curious if you could expand on that and whether either of the other panelists could do so.
Sounds good. I guess I'll go to John first, Wake, and then
the first two would be useful for actual aerosol dispersion missions. And what you'd probably do if you liked the results of the first two is you'd probably build a handful more like those, sort of what we call low rate production of maybe 6 to 10 of those, which are sort of more handcrafted, less automated in the production, but lower setup costs before you moved into the rate production, which is mostly in the tooling and today the level of automation in the production line that you do.
Wake? So there was a question for you, Wake, about your comment about being skeptical about the emergency framing. If you want to expound on that for a minute, that'd be great, and then we're going to wrap up.
So I don't favor the idea that this is plan C in the event that everything else falls apart. We ought to be undertaking research on this deliberately and relatively soon so that we're able to present the world with sensible options. I think a way that solar geo could go very wrong is not to do much research, find ourselves in an emergency, and suddenly lurch without sufficient evidentiary basis, as well as you, David, are one of the key proponents of. We should be seeking to ramp up slowly rather than turn some binary switch and hit the planet with a climate hammer. So both of those considerations, I think, argue against the emergency framing of this and call for it to be a program developed deliberately over time and leave sufficient time for wise decision making about it.
The only thing I would add to that is you only get a benefit to deploying something like this if you're capable of sustaining that deployment over a really, really long time. And that means you have to have broader consensus than just, say, one small group of people saying this is an emergency. And so that's a challenge, right, with who gets to decide that it's an emergency. And if that is not widely held, then you don't necessarily get the sustained credibility and support and legitimacy that would allow you to actually reduce impacts.
Yeah, I would just add on that this is a problem that does not require the might of the U.S. government alone to solve. There are many people, many of you in the room are in organizations who could, should they decide to do it, deploy the resources to make this happen. There are many other countries. There are NGOs. It will be fascinating to see how this plays out.
On that note, it will indeed be fascinating to see how this plays out. Thank the panel